Good. Good morning, everybody. Well, the only thing that stands between you and the excursion, except lunch, of course, is a morning of market risk, and we hope we can make this an entertaining interlude, so to say. The good news is, of course, for those of you who feel already exhausted, what we do today will use what we've developed so far, but it will not be used tomorrow and on Friday. So in that sense, tomorrow morning we'll have another fresh start. As you can see here, it is chapter 9 in the book, and that's why it's also chapter 9 in the slide. Some of chapter 8 will come then, 7 and 8 will come tomorrow morning. So we took the liberty of exchanging the order for pedagogical reasons. We've divided our treatment of market risk management into 3 sections. The first one is what will keep us busy before coffee, risk factors and mapping. So in our introductory session Monday morning, we took a very quick look at mapping, but basically all we did was writing down a formula of the type, still asleep? Wow. Either they don't react or they do too much. Writing down a formula of the type, the value of the portfolio is equal to some function, I think we called it G, of time and some risk factors. And then we developed some formalism for it. But except for the very simple example of a stock portfolio, which basically served to introduce or explain the notation a bit better, didn't really work with that. So the big question mark is, of course, the choice of G and Z. And as you can imagine, that is typically a trade-off between tractability on the one hand and precision granularity on the other. If you want a very detailed analysis where you take every feature of a product into account, you will have a complicated function G and you will have very many risk factors. That's maybe not so practical for a large portfolio, but maybe exactly the right thing when this detail is needed. So maybe you're measuring the risk of a trading desk in derivatives that deals just in whatever interest rate options on Swiss bonds, and you want to measure that risk, then it should probably take all features of the products into account. When you're maybe doing market risk management for a whole bank portfolio or a whole asset portfolio of a big insurance company, maybe not every early exercise option of some exotic interest rate product is that important. You need a broad brush approach to keep the whole thing tractable. And we will, in particular when it comes to interest rates, give you sort of examples of both approaches. And in particular, Alex will, so this is really precision granularity versus tractability. And so the idea of this first session this morning is not to solve this issue in detail for every conceivable portfolio, but to give you to go into a little bit more depth there, to give you some ideas how such a mapping could look like, in particular for bond portfolios, also a little bit for option portfolios, and to show you how the factor modeling, which we learned yesterday, can be used if you have, say, for instance, a large dimensional bond portfolio with many bonds to still ensure tractability and to get the number of factors down to a reasonable level. We will focus a lot on bond portfolios because, of course, that's maybe the most important asset class insurance companies are investing in, and so bond portfolio management is important in that context. Good. That's the first part. After the coffee break, we will look a bit more in detail at market risk measurement. So essentially what we're going to do is we're going to revisit these three methods for evaluating loss distributions, the variance, covariance method or analytical approaches, and historical simulation. Talk a little bit about, in particular when it comes to historical simulation, implementation issues related to quantile estimation. We'll talk also about how time series considerations and the time series models, which we discussed Monday afternoon, can be used in that context to deal with the issue of time-varying stochastic volatility, which we've seen that this is present in our analysis of gauge models. And the last bit, the second half of the session after the break, is concerned with backtesting, so with testing your models. I mean, this is of course not enough just to set up a model and to compute value at risk numbers. You also have to check if the predictions of your model are sort of halfway in line with reality, and you have to do it for internally, and your supervisor also forces you to do it. And Alex will present you some ideas as to how to do that, some sort of standard methods, but this whole area has been revisited recently, bringing in some concepts from prediction and time series analysis, such as elicitability. Yeah, that's a difficult word at this time in the morning. And so he will tell you a little bit about that. Being the person who starts off the day, I have the pleasure of promising a lot of things my colleagues will do. That's great. Good. So that's what we plan for this morning. Risk factors and mapping, the loss operator. So let us revisit the terminology we introduced earlier. Okay. We introduced on Monday morning. The key idea is that of a loss operator. The loss operator was essentially the object that mapped changes in risk factors onto losses or profits and losses of the portfolio, because a key insight from this Monday morning general notation was that essentially what you have to look at if you use this mapping here are changes in these risk factors, and I need to understand how changes in risk factors, given a choice of G, affect changes in the value of your portfolio, and then you have to evaluate the loss distribution. The current time is t, so we're always standing at time t, and we have a time horizon of delta t, so t plus 1 is the next time point, and the time difference between these time points will be delta t. We assume that, okay, we're not going to talk so much about what you do when you go over. So this could be, think of it as one day. We're not going to talk about so much today what you should do if the time period is longer, like 10 days or 1 month. Maybe you can then apply some scaling rules. We fix first the simplest setting. We assume that the portfolio doesn't change, which again is only reasonable if we consider this delta t to be short. And we assume, of course, that the value at time t plus 1, vt plus 1, is random. Our goal is to determine the loss distribution. So Lt plus 1 is the negative change in value, and we will use a mapping of the form value at time t is a mapping of the risk factors and some tau t. Now why do we have tau t here? Here I still wrote t. That is an issue which we glossed over on Monday. We have sort of two ways of measuring time, and that's why this tau t comes up here. On the one hand, it is natural sort of to measure times in days. So this is the day 1, this is day 2, day 3, and so on. On the other hand, when you think about bonds or options, then typically there you don't measure time in days, you measure time in years, and everything is quoted in terms of years. Interest rates are quoted in years, volatilities are quoted in years. And this tau t is essentially the link between these two. So tau t is going to be, that's also be on a slide later on, tau t is going to be equal to t times delta t, and that gives us sort of in real time, in years. So if we go t periods ahead, then this gives us what this means in years.
Sorry, I don't get the dimensions there. You have time to the left and time squared to the right.
No, this is not really. This is like, this is calendar time. This is not a time, this is a number, so to say. This is the number of days in the future. Maybe it would be better, but for some reasons, because in time series, it might be better to have an n here. But for some reasons, because it's time series, think about this here as n. This is a number of days. And then 10 days ahead means so and so many fraction of a year. That's what this is meaning. So if we are measuring time in days, so delta t is 1 day, and if we have 250 trading days, then this could be equal to 1 over 250, and then 10 days ahead would be 10 over 250 years. That's the idea. I know we struggled when we wrote the very first, it was the first, basically that was when we started to write the first edition of the book. I started to do these things, and it was the first big obstacle we sort of ran into how to solve this satisfactorily. And, but you need it when you think about derivatives and bonds and so on. Good. So tau t is the time in units of this valuation time. So typically in years, and delta t is 1 day. Good, that's the issue of time. Basically what is written all down here. And tau t plus 1 minus tau t is then simply delta t. So that's the difference between two multiples of the risk management horizon. Okay. The risk factor changes are then xt plus 1 equal to zt plus 1 minus zt. There nothing changes. And then we have, as on Monday, the loss lt plus 1 is negative change in value. That is g of tau t plus 1 zt plus 1 minus g of tau t zt. Now we have to sort of put the valuation time into this valuation function. And of course, this is, if you bring in the differences, minus g of tau t plus delta t, zt plus delta xt plus 1 minus g of tau t zt. And if you look at it, again, the only unknown thing in this difference, as seen from time t, is this xt plus 1 here. And that's why we can view the loss as a function of the risk factor changes. And because this view is so important, and because this is a very convenient piece of notation, in particular when we want to explain various ways of historical simulation, we've introduced a piece of notation, and this piece of notation, we've given it a grand name. It's a loss operator. Don't tell your boss that you're going to apply a loss operator to your portfolio. He might not like the idea, but it's something very simple. The loss operator at time t is small lt of x, and that gives us the change in the value, no, the loss, so the negative change in the value of the portfolio when if the risk factor change is equal to small x. And now we've changed to small letters here, assuming that we know the risk factor's realization at time t. if you do it like that, yeah, it's the idea of the full revaluation. So it means to compute this loss in this way, you have to value your portfolio at time t, and you have to really do a full revaluation at time t plus 1, not only something approximate, which can be complicated if you think about a portfolio of many exotic options, which you cannot price analytically, but you would need to use Monte Carlo for that. Then computing this thing can be a quite complicated issue. Now, from the point of view of statistics, of course, what do you need to know to get the distribution of this LT plus 1 here? LT plus 1, as you've just seen, is a function of the risk factor change xt plus 1. So what we need to understand is the distribution of xt plus 1. Here, an issue pops up, again an issue which I ignored on Monday, but which we should discuss now, given that we looked so much at the time series. There are two ways, sort of, two types of distributions of xt plus 1 we could use. On the one hand, we could say, so think about a very simple, take the simplest example conceivable, assume it's one stock, and the risk factors would be log returns, and we have this valuation, and so xt plus 1 is a log return, and we need the distribution of this log return. And now think about all the stuff Alex did with you on Monday afternoon on the gauge modeling, where I think he really managed to convince you that there is stochastic volatility in time series and that we need to model these things. And so, on the one hand, we could say we want to use the conditional distribution of xt plus 1 given all the information we have so far. So in the context, if you use a gauge model, for instance, to model the log returns, that would be the current volatility times the would be the innovations distribution, so the distribution of these normal or t or whatever he had to construct his gauge model, multiplied with the current estimate of the volatility from period t to t plus 1. So if we are in a period of high volatility, you would have a different distribution, one with a larger variance than in a lower distribution. So xt plus 1 would be distributed. Now help me. The volatility from t to t plus 1, was it sigma t or sigma t plus 1? Sigma t plus 1. So it would be sigma t plus 1 times the z, and the z is this innovations distributions, and that t plus 1. That's the distribution of these noise variables we use to construct the gauge model with. So say this is normal. That's the volatility, and that's a function of xt and so on. So that's known at time t. And if sigma t plus 1 is large, we are currently in a market is nervous, we have seen a couple of large price movements recently, our gauge model points to a high volatility, then we would have a different variance than if it was small. That is the conditional loss distribution. Alternatively, you could say, well, I want to take a little bit more of a long-term view, and we've learned that these gauge models, for instance, the xt has also, the model has a stationary distribution, is strictly stationary, at least if alpha plus beta is smaller than 1, then it was both strictly and second order stationary. You could say I take the unconditional stationary distribution, and I do not care if I'm currently in a high or in a low volatility environment. That would be the unconditional risk, unconditional distribution. We're going to come back to this issue a little bit after the break when we discuss various ways of using historical simulation where this distinction also matters. And there is some debate which is the right way to go. It is a little bit similar to the debate, those of you who have ever heard about credit risk modeling, where you ask yourself also, should you use ratings, or should you use values of credit risk which are taking exactly the current situation into account, if the economy is in a recession or in a boom, or should you take a longer term perspective? There is no unique answer to that. In pricing, it's clear when you price or value something, then you should always take the condition. You should take every information you have, and the price is the sort of the best estimate or something given all current information. So for pricing, it would always be the conditional distribution. But for risk management or for capital computation for purposes of computing risk capital, the situation is not so clear. If you take the conditional distribution, you use all information, but you will get largely fluctuating capital requirements. If the volatility is high, you need a lot of risk capital. If the volatility is low, you need little risk capital. Of course, if you take a larger portfolio, things average out to some extent, but volatility across different markets tends to be correlated as well, and so typically if one market has a high volatility, so others have it, so also your aggregated bond portfolio or stock portfolio will tend to have some stochastic volatility. I mean, an example for that is if you take an index, which is sort of an aggregation of various stocks, it still has stochastic volatility. And so you would need, you have largely fluctuating capital requirements, which is not so pleasant in a sense, because well, what should you do? Either you leave a large safety buffer, or you would have to raise capital all the time, which is difficult, or you would have to change the portfolio composition all the time, scale down your position whenever you're in a high volatility environment, which is also not so easy. So in that sense, for capital, for the purposes of computing risk capital, maybe taking a longer term view might also have the benefit of leading to more stable capital requirements for pricing, or if you would just have a very small desk or so, then you would definitely want to do the conditional method. What matters for us here is not to tell you you should do this or you should do that, but to make you aware of the difference. Good. Now, we were already, on Monday, we looked a little bit at delta and delta gamma no, we didn't look at delta gamma, but we looked at delta approximations. So if the mapping function is differentiable, delta t is relatively small, you can approximate g with the first order Taylor series approximation. This has a number of advantages. It gives linear expressions for the change in value of the portfolio. You don't need to revalue your portfolio in full. You need just to compute sensitivities. And in some cases, we also get much nicer formulas for the change in value than when you do the nonlinear expressions. So the change in value in the first order Taylor approximation, g of tau t plus delta t zt plus x is equal to the current value plus time derivative. Now we have a delta t here. That's because this function measures time in years, say, and the derivatives with respect to the risk factors. And if we go to the loss operator, we get this loss operator notation, LT delta of x. It's basically the same thing. That's linearized loss operator. And we say, okay, what is the linearized change in value of the portfolio if we observe the risk factor change x? And this first guy here, you can sometimes omit because delta t tends to be small. As an example, consider European call options, so the very simplest derivative portfolio you may consider. We have one standard European call on a non-dividend paying stock. Maturity time t, say in 3 months from now, exercise price k. We use the Black-Scholes model to value this option. We simply use it as a valuation tool here. We're not discussing if the underlying assumptions are correct or not. We're simply accountants, and we have this miraculous formula. We looked it up in Hall's textbook. And so we use it. And so given current stock price, given the current interest rate, given the current volatility, whichever value we take here, the price is given by this expression here. So S times phi of D1 phi is standard normal distribution function minus the discounted stock price times phi of D2. And these arguments D1 and D2 are given here. They depend on logarithmic difference of stock price and exercise price, interest rate, time to maturity, and most importantly about the volatility. And the D2 is the same type, only that you have a minus sign here. You can derive this formula under special assumptions that asset prices follow geometric Brownian motion. But as I said before, we just use it. In particular, when you use it, you can also say, well, while it's derived on the assumption that interest rates and volatilities are constant, I can use it as a pure valuation tool also in an environment where these things change. And in real markets, of course, interest rates and in particular volatilities do change. So it's the question which volatility you use. Typically in practice, you would use implied volatility. So this might be an option with an unusual S and with an unusual strike or an unusual maturity, but there might be other options with more standard parameters traded. You can use those to infer the volatility the market. You can back out the volatility the market uses to price those, and then you would have a market estimate of volatility, and you can plug that into this formula. And if you do this and you look at historical time series of volatility, you see that these things change. Good. So the risk factors would be logarithmic stock prices, interest rates because they change, and these volatilities we use as an input. And the risk factor changes would be then log returns on the stock price, interest rate difference, and changes in volatility. The mapping is just value at time t is the Black-Scholes formula at time tau t. Again, here, all inputs and also time to maturities would be measured in a multiple of years. So if you have 3 months to go and if you use a standard implementation of the Black-Scholes formula, you're not supposed to say 3 months is roughly whatever 60 trading days. You should put in 3 months is 1/4 of a year into this formula. That's why we have the tau t here. And then that's the value and all the other things you put in. And for this portfolio, one would use a linearized loss operator. This gives this expression with all these derivatives. Now, if you go to your colleague in the trading department and you show him this formula, he would say, now you've gone completely crazy. I knew before that you can't trust these actuaries, but now I know it for sure. Because nobody would talk about G, Z, I, and G tau. These derivatives have names. And these are these famous Greeks in option pricing theory. So you would write the linear loss operator time derivative, which is known as theta of the option, plus the derivative with respect to underlying stock price. Now there's an additional ST here, which comes from the fact that the delta of an option is the derivative with respect to the price. Here we need to take derivatives with respect to log price. There's a second differentiation, and that's why we get the S here. Times the first change in risk factors, the rho, which is the change in interest rate, times the second change in risk factors, and the vega, it wasn't really Greek, but that's how the derivative with respect to volatility is known on markets, times the third one. So the Greeks do play a huge role in managing in computing these loss operators, and the most prominent one is, of course, the delta, which is this term here, which is why the whole thing has this delta abbreviation up here.
Can I make one remark here, because this came up in conversation, perhaps if we could just go back one page. This is the decision with respect to what are the risk factors and how you measure the risk factor changes. I mean, for the prices, we've taken log differences, but what you do for the interest rates and what you do for the volatilities is a matter of debate, how you define the risk factor changes. And so you've taken simple differences here, but you could do something else.
You could also consider log volatilities if you wanted.
You could also consider log changes in implied volatility. That might be nice because volatility shouldn't become negative, whereas interest rates might.
Yeah, volatility shouldn't. Then you've got a real problem.
So it's not that it has to be done this way. There's always a decision as to how you define your risk factor changes. Log differences, relative or absolute differences, simple differences.
Yeah. Well, now of course, you may go one step further and consider quadratic approximations. Well, I beg your pardon that I'm now at a business school, and Vienna University of Economics is not a pure business school, but it's a business school in the sense that we do not have blackboards anymore, only whiteboards, so I cannot resist the temptation of occasionally using a blackboard. Now, of course, if you take our call option, say this is K, this would then be the, this is S, and that would be the value. So this is S minus K plus the payoff of the option, and if you look at the price of the option, it will always look somehow like that. That's the option price. And now, what we do in a first order approximation, so when you do linear loss operators, we approximate the change in value by this tangent line here. And now you could, of course, say, well, maybe at least for small changes, I can do even better. For very small changes, this is good enough. For medium changes, this is maybe not so good because this function here is convex, the option price, whereas my approximation is linear. So you might consider second order approximations where you have then some sort of a parabola. So this would then maybe look like that. And you would then have, so this, too many lines here now. This would be the linear approximation. Improve the quality of the approximation, and this would then be the quadratic approximation. And for that, what you have to do is you have to go to a second order Taylor approximation, basically. And your hope is that, well, for very large changes in the underlying risk factors, this quadratic approximation may be completely nonsense. For small ones, it's definitely good because the linear one was already good, but it would perhaps be also good for medium ones. And improve the quality of your approximation. And if you expect very large changes, then the whole linearization idea is not working anyhow. Good. So we may go one order further and go to second derivatives. Add some notation for that. If I show it here, I have to go over here. So omega are the mixed partial derivatives with respect to time and the risk factors. They're not so important, we'll lose them anyhow. Gamma is the matrix with the second derivatives of the option price of the portfolio value with respect to the risk factors. So gamma sensitivities would be, in option pricing terminology, the derivatives twice with respect to the underlying risk factor, and cross gammas are the mixed derivatives. Well, I still remember that. I mean, Alex used this slang, but I remember when I was a young postdoc coming from university and I was visiting UBS because I had a position sponsored by them, and those days they had problems with their portfolio of basket options. And the trader explained this to me, that she told me that she didn't get enough compensation on her cross gamma. It took me a while to figure out what that meant, and in a sense it meant that they took too low correlation parameters in their portfolio, and that's why the change in the model is not, was not enough for what she saw in the market. So she was right, but it was a typical example of the slang I think you encounter when you go to these trading desks. Good. So when you do a full second order approximation, we have this first order term, so that's first derivatives plus 1/2 second derivative with respect to time times delta t squared, plus the mixed derivatives, and then the second derivatives with respect to the underlying risk factors, x transposed matrix of second derivatives times x. Now, if you look at that thing here, you have terms of different order. I mean, the whole idea, of course, is to do this for delta t relatively small. Otherwise, these approximations don't make sense. You have terms of different order here. Good, this is clearly of order delta t. The risk factor changes themselves are typically of order square root of delta t, so larger, because the variance of in a continuous model like Black-Scholes but any other continuous diffusion model for stock prices, also the stochastic volatility, somehow the variance of the price changes over small time periods is proportional to delta t. And so if you scale by square root of delta t, you get something sort of finite. So the price changes of order square root of delta t. You have terms of the order delta t squared. You have terms of order that would be square root of delta t times delta t. And here these are square root of delta t times square root of delta t. So if you take a physicist's mind and say, okay, well, I care only about terms of order delta t or larger, you could say I'm dropping all these things which are of order delta t squared or order delta t to the power of 3 over 2, and you get a slightly simpler formula, namely minus the change in time, which is now delta t, plus the linear loss operator, which is basically of order squared of delta t, plus this gamma term, which is also of order delta t, which is a bit simpler. You can do this for the European call option, and the quadratic loss operator then takes this form for the linearized one, minus 1/2 times these weird gammas and these cross gammas. They have obscure names. We do have, if you want to play with S+, we have a script where you can see that the approximation gets better if you do this, then the linear loss, as soon as the risk factor changes are of not too large, so if they are of a small or moderate size. If you wanted to do some simulation, you would see that it clearly improves things. But I promised that I would talk a bit about bond portfolio, so I have to hurry up anyhow to do at least a little bit of that.
Can I ask a question?
Yes, of course.
I mean, this delta approximation is really important in the context of the Swiss solvency test, since there are many Swiss people here. The question that I have when I look at the implementation of FINMA, and maybe FINMA people can help there, when you are forced to compute your derivative there, which in principle is a limit where you take an interval going to 0.
Yeah.
Actually, you're forced to compute it with a quite large interval. I mean, a delta, I think it's 100 basis points for your interest rate, for example. So basically, your derivative that you're computing is not really a derivative. How important is that? And why did FINMA choose to use such a large, impose to you to compute your derivative with something which is far away from being a limit?
Well, maybe, is somebody from FINMA here? No.
Could as well go in the opposite direction. Okay. To me, that's not really an explanation. I mean, you're making
A reason, a potential, well, okay, the one answer is, of course, if it matters or not, that depends always on how nonlinear your valuation function is. If it is very nonlinear, if you take sort of difference quotients, which is what FINMA does, so they really say, I mean, you have f, so the derivative, say f prime is equal to, sorry for doing first calculus, f of z plus a minus f of z divided by some h. Good, that's the limit. Now, of course, when you do this, when you compute it, and you really compute it by taking this difference approximation, and you maybe even compute this f here via doing something like Monte Carlo, because you divide by this small h here, if you get this difference slightly wrong, you might get your derivative very wrong. So computing difference quotients for slightly larger h might have the advantage that the numerical approximation is more stable, even if it's not exactly the derivative. This could be one of the reasons, and of course, if it really matters, depends on how nonlinear. If this is a linear function, it doesn't matter at all. If this is very nonlinear, it matters a lot. But then the question is, how good is the linear approximation? I mean, the thing is probably a little bit that all this methodology of this delta gamma approximations and so on, it has been developed by banks for market risk management for derivative portfolios and for time horizons of 1 or 10 days, where these risk factor changes typically will be small and so on, and where this makes a lot of sense. Probably if you go over a 1 year horizon, the whole thing is a little bit questionable anyhow, but probably done for tractability. Good. Alex is getting nervous with respect to time now. Bond portfolios, good, at least a little bit. P of small t capital is the price of a zero coupon bond, and for simplicity, we assume that any bond zero coupon bond we're considering here has a payoff of 1 at time t. They are default free at the moment, so they pay 1 for sure. Default risk will be treated tomorrow. We measure time in euros. Now, zero coupon bonds themselves are traded, but they are also very important theoretical things, because many portfolios, coupon bonds or asset liability portfolios can be considered as linear combinations of zero coupon bonds. So if you understand how to deal with a portfolio of zero coupon bonds, swaps also, we sort of understood a lot about risk management for many other interest rate products as well. Now, okay, you need descriptions of the term structure of interest rates. You could consider the mapping that matters the maturity date or to the current value of the zero coupon bonds, but that's something nobody really does. Instead, yields are being used. That comes on the next slide. Of course, bond prices at time t are assumed to be known. In practice, that is an issue, because if you want to construct your curve of zero coupon bond prices, you have only a few of them traded directly. You have to compute other numbers by stripping them from, so by taking zero coupon bonds which are traded or swap yields which are traded and computing the zero coupon bond prices that would yield to the quoted swap spreads or coupon bond prices, and then you have also liquidity premia and all these things. If we wanted to do this in detail, I would spoil this beautiful morning, so we omit it. But it's not completely trivial either, as those of you who work in this area definitely know. But from first principles, of course, you could say this is known, or it is at least roughly known, but what is random is, of course, how do bond prices look like tomorrow or next week. So the future term structure is not known. And what is important, that's why it's good that this is done here explicitly in this notation, is always, when you look at bond prices or yields, then always in the first component, that's where time enters, that's where randomness enters, and that's where these things are sort of random. The second argument, that's just time to maturity, and there they are typically smooth, so it's important. Time is always the first argument. Good. Typically, you would not express you have very little intuition about bond price. Zero coupon bond price with a face value of 1 and 1 year might be in the current environment. Well, if it's a German zero coupon bond price, this might cost you €1 and 1 cent because you have negative interest rates, or you might have 99 cents or 98 cents, and if it's longer maturity, 96. It's difficult to have intuition. We all have more intuition about yields or interest rates. That's why the typical risk factors considered are the yields continuously compounded or not, and the continuously compounded yields are given here. It's the log bond minus the log bond price divided by the time to maturity. If you ask yourself, if you see this for the first time, why, then it comes from the fact that you ask yourself, my current bond price is P of small t capital T, and what growth rate at maturity it will be worth 1, and what sort of the growth rate when I have continuously compounding do I need? So x buff t minus t y of small t capital T is equal to 1. That's the equation for the yield. So if you ask yourself, what growth rate do I need to explain this bond price? And if you solve this, you get the yield. Okay. And this is the yield curve at time t, which is typically the mapping, the time to maturity date going to y of small t capital T is referred to as the continuously compounded yield curve at time t. Very often one puts here also not the maturity date, but the time to maturity. And the advantage is, of course, that yields are comparable across different times to maturity. You can make statements of the yield of a 1-year zero coupon bond is 1%, and a 2-year zero coupon bond is 1.5%. Much easier than for prices. Good. And if you have a whole portfolio of bonds, and if you want to look at this portfolio in very much detail, then we could use yields as risk factors for all times to maturity. Obviously, if you do this and we consider just yields at to maturity, all these bonds are denominated in the same currency, say Swiss francs for simplicity. Otherwise, we would have to introduce risk exchange rates as risk factors as well. Good. Lambda I is the number of bonds with maturity in the portfolio, so that the value of the portfolio is sum I equals 1 up to d lambda I times the current bond price, and using our expression that the bond price is x of minus maturity date minus the current date, so minus ti minus small t times y of small t capital Ti, the relation between bond prices and yields, we get our very detailed mapping. So we would take all yields as risk factors. Good. And we can put this into our mapping notation, where again time would be computed in years, and then this would be the function g here. This. It's written here. Good. The portfolio loss. I go through this. The computations are all elementary. So the portfolio loss is just minus the change in the value of the portfolio. And if you look at this equation here and look carefully which things can be factored out, you get this expression for the portfolio loss. And if you go to standard bond pricing notation, you get this loss operator here, where you see the yields in here, and the xi are the changes in the yields. So for each bond has a maturity, and the xi is the change in the yield of the IF bond. This may be too much if you have many bonds there with different times to maturity, and that's why Alex is going to explain you later on how to reduce the number of factors in such a modeling to a few number of key factors, but first we consider the detailed analysis. we get something more interesting if we consider linearized losses. The first derivative of the mapping function with respect to time is this one, with respect to the changes in yields is this one. And so please bear with me if I'm not doing all the computations here in detail. They are elementary. What you get then for the first order approximation is this expression here. And you can compute second derivatives, of course, also. Their square time to maturities enter, and so that those are the second ones. Good, and then we can compute the quadratic loss operator also. What is interesting is not so much these formulas per se. What is interesting, and what I would like to spend the remaining 5 or 10 minutes I have on, is the relation of these formulas to tools which are standard in the management of bond portfolios, in sort of pragmatic management of bond portfolios, namely duration of and convexity. We start with duration. When you consider risk management or via duration, you make the following simplified assumption. So here is time to maturity, say t minus t. Then you would have here a certain yield curve. So typically they are slightly increasing. So the yield curve could look like that. Maybe this is then 0.5%, and this would be then 2%. And this is y of at small t, and then capital T minus small t, something like that. Yields, you can express them either in days or in times to maturity. And in a very simple, now if you think about it, the first order risk, or the most important risk, is in a sense really that interest rates can go up or can go down. So in a very simple model, you could say, well, tomorrow my yield curve is either going to look like that, or it's going to look like that. So there are only parallel shifts in the yield curve possible. You may say this is stupid. It's not completely stupid, of course. If you do, I don't know if you will have time for that because now I'm talking so much, but otherwise you find it in the book. If you do a principal component and the analysis of the changes in yields, then the first principal component, the most important change, is exactly this type of parallel shifts. But of course, more can happen. If this was the only possibility, the yield curve would always look like that. It can also turn around and so on. But in a simple world, you would say that that's the most important risk factor, and you consider only parallel shifts of the yield curve. So that means that the y of tau t plus 1, the yield curve tomorrow, is, say, the yield today plus some x, and the x is the same, independent of the ti. That's the important part here. So we have only parallel shifts. And in that case, this means zt plus 1i, zi plus xt plus I. So we have only parallel shifts in level. And that means that this formula for the loss operator, the linear loss operator, simplifies a lot, because these xi's are no longer xi's, but now they're the same for every I. And this allows us to write this in a simpler way. And if you do that, what you get is, that the loss operator will depend only on x, the change in the level of the yields, And if you do the computations, which are not difficult, you see that the linearized loss operator can be written as minus the current value of the portfolio times AT delta t plus dtx. This first term here we don't have to worry about a lot. That's time derivatives. Delta t is small, so ignore it for the moment. This one, on the other hand, the dt is quite interesting. D stands for duration. And so many of you will know this, of course, so please bear with me for the others. But if you haven't heard it so far, it's important. The duration, or Macaulay duration, is a weighted sum is given in this formula here. Now, what is this? It's a weighted sum of the times to maturity. And because these are weights here, if the lambda i's are all positive, then these are really positive weights, because the current value of the portfolio is sum I equals 1 up to d lambda I p of tau t t I. So these guys here really sum up to 1. And you weigh the time to maturity with the value of this. So if you have a large position of bonds with a certain time to maturity, say a large position of 1-year bonds with 1 year maturity, then the time to maturity 1 year will get a large weight in this expression, and so on. And given our linearized loss operator here, this term I said we ignore. So if we agree that the most important risk factor change are these shifts in yield curve, then we would say over small time horizon, the losses in our bond portfolio or asset and liability portfolio are proportional to the duration times, proportional to the duration times x. So the losses are roughly equal to Vt dtx. And this means that if it depends now on the sign of the whole thing. If dt is positive, which is the case if you have only cash flow, if you have no short positions, if you consider only asset positions, then that means that increase in level of yields leads to losses, decrease leads to gains, of course, because the increase makes the loss bigger. If x is positive, then the loss will be bigger. That's clear. Higher interest rates means losses on bond portfolios and the other way around. And how large this is really depends on the duration of your portfolio. So at the first order, the duration gives you the sensitivity of the portfolio value with respect to changes in the level of interest rates. It's clear also intuitively if you have long-term bonds, the duration will be large and they will be much more sensitive to interest rate changes than short-term bonds. What is interesting about the concept of duration is mostly if you take the whole thing works also if some of these lambdas are negative. So if you have either short positions of bonds or if you consider assets and liabilities. So assume you're a pension company and you have sort of fixed payouts to make in the future every month, and these are your liabilities, and you have assets and you have to invest them so that you're able to pay out the pensions all the time. And so if you take the whole thing together, you have assets and liabilities, and you want to do this, you structure the bond portfolio. You have a sum, and you want to structure, you invested in the bonds, and you want to structure it in such a way that the overall value of your cash flows are relatively insensitive with respect to changes in interest rates. And you might try to do this so that the duration of the overall portfolio, well, now some of the lambdas are of course negative, is equal to 0, because then you're protected against small changes in level of the bond portfolio. That's basically what is written here. And you call this also immunization. This is of course not a completely satisfactory thing, because there may be also more complicated changes in the yield. Yield curves can twist. That's the one thing. The other thing, it's a first order approximation. You may go one step further and do a quadratic approximation. You're still living in that simple world where there are only parallel shifts in yield curve, but you're a little bit more sophisticated in the sense that you take also a second order approximation of the relationship between yields and bond prices, and this gives a slightly better approximation. and then you get another term in this approximation. Duration remains in the quadratic loss operator, but you get the CT in here, and CT is the so-called convexity of the bond portfolio. That's always positive. Now you take the square of this, it's a weighted sum of the square of the times to maturity. It's always positive if lambda i's are positive, otherwise not. And you can use this for refinement of the whole thing and ask yourself, so if you have a portfolio which is immunized in the sense that duration is 0, then the convexity will tell you how it reacts to changes in the interest rate sort of as a second order correction. Okay, I won't go into detail there, but I will rather hand over to Alex, and he will then take this a step further and show you what you have to do if you have a really large bond portfolio and you cannot take all the yields as factors because this would be too complicated.
Okay, so if you go to 9.1.4, so we've got two extremes here. On the one hand, this parallel shift model is unrealistic in practice, that the only thing that can change about the term structure is the level. On the other hand, if we have large portfolios of bonds, then such the overall position in fixed income instruments at a bank, then modeling the changes in all the yields for all the different times to maturity in the portfolio, that's going to be tedious, impractical perhaps. And then there's another statistical issue. Remember that xt plus 1 is the changes in risk factors. The risk factors would be all of these yields. So we're looking at the changes in yields. They're going to be highly dependent. You've got fractions of years, 2 years, 3 years, longer maturities. They're going to be, these changes in yields are going to be profoundly dependent. So it's quite difficult to estimate a statistical distribution when you have these high levels of correlation, sort of 80-90% correlation. So we want to reduce dimensionality, and this becomes an interesting application for the factor modeling techniques. Both the fundamental philosophy and the PCA statistical philosophy. I'm going to start with the fundamental factor modeling philosophy. And we're going to build a factor model that reduces dimension from, let's say, D, that's the number of maturities we have, down to 3, which is bigger than 1. If you like, this parallel shift model is a reduction of dimension to 1. But that's a bit extreme, so we'll go to 3. And of course, if you know about bond portfolios, you'll know that we tend to talk in terms of changes in level, changes in slope, and changes in, changes in curvature. So 3 factor models. In practice, often the 2 factor models are quite good. So this Nelson-Siegel idea is quite old, but I came across a nice R library which estimates the Nelson-Siegel model, so I decided to try this one out first. The idea is this, that basically this isn't really an equals, it's an approximation. We're going to say that all of the yields for the different, or the term structure can be modeled in this way. So the yield, tau t is current time expressed in years typically. T is the maturity, this may vary, but it can be expressed in terms of 3 terms. So 3 risk factors. ZT1, ZT2, and ZT3. And the first risk factor that is multiplied by 1, but here we have functions appearing. Functions K2 and K3. You can see the form of the functions. These are the forms that were suggested by Nelson and Siegel. Other authors came along after Nelson and Siegel and suggested other functions, alternative functions. In particular, Svensson has a model with 4 factors. But we will just look at the Nelson-Siegel model, although the software I use also contains Svensson's model. So these are the forms of the functions. There is a parameter eta, which basically adjusts the, well, these are the functions here. So it's going to adjust the slopes, and it's going to adjust the position of the maximum. I forget which one is which. I think this one is K2. And this one is K3.
And we will talk a little bit later about where this eta value comes from. This is actually an estimated value. So this is a three-factor model. All of the, sorry?
First factor is just the change in level.
Yeah, so this is going to represent the change in level. This factor is going to represent the change in slope. This is going to represent the change in curvature. This isn't immediately apparent. We have to perhaps do a little bit mathematics on the next slide to see that that makes sense, at least in the case of the first two. And so this is a model. This is an assumption. This equals here as an assumption. It's a model for the yield curve. Beg your pardon? Well, it could be. It could be time dependent. We could allow a different eta every day, or we could look for an eta value which works over time, a good value of eta which seems to work over a long period of time. And when we come to look at the software, we'll look at those two options. I beg your pardon? Capital T is the maturity. Tau subscript T is current time. And the only strange thing about this notation is we are measuring current time in units of years. And typically today, we're looking at the yield curve today. So T is today. So this T is today, and T plus 1 is tomorrow. And the length of time between today and tomorrow is delta T, which would be 1 over 250, if a year consists of 250 trading days. On the other hand, if we're looking at changes in the value of our bond portfolio over 1 month, then tau T plus 1 minus tau T would be 1 over 12. Yeah, so this interpretation that Rüdiger mentioned, eta is a tuning parameter. Why is the first factor level? Well, you have to think about the limits of these functions as s goes to infinity and as s goes to 0. Well, you can see what happens as s goes to infinity and s goes to 0 with these functions. But if you let the maturity time, big T, go to infinity, then y converges to ZT1. So that's why ZT1 is interpreted as a level factor or a long-term level factor. And if, on the other hand, you consider this difference, so the limit as t goes to tau t minus the limit as big T goes to infinity, well, this difference in limits is ZT2, so that's why ZT2 has an interpretation as a slope factor, difference in short and long-term yields. And I haven't written down the details, but the ZT3 has an interpretation as a curvature factor, if you look back to the original paper. So we will try and estimate this model. Why do we do it? We do it because we can reduce dimension down to 3. So for example, the portfolio mapping function, we can work out what it is under this model, so we can recompute, go through the algebra and work out what's the portfolio mapping function. And these loss operators, and their linear versions or their quadratic versions, obviously they become functions on 3-dimensional space rather than functions on d-dimensional space. D is the number of bonds in the portfolio, 3 is the number of factors we reduce to. So how do we do it? We need to determine the factors. Now, this is a situation where these factors here aren't directly observed. We observe the left-hand side, let's say. We have data on the yield curve, but we don't directly observe the factors. So we have to estimate the factors. That's why I say it is like a fundamental factor model. Getting the wrong. Okay. We require values for these factors. We have to overcome the fact that they're not directly observed, so they have to be estimated. So we have data. So we're going to analyze data of this kind. we have, how is this to be interpreted? The data vector at time t, it consists of the yields for m different times to maturity, S1 and Sm. Okay, so we have a long vector here. M is large. And that's what we're going to analyze. And this is how it fits into the factor modeling setup. So this is what we're observing, the yields for all these different times to maturity. BT is known because the BT matrix comes from the Nelson-Siegel functions, or at least BT is known if we fix eta t. There's a little problem here. If we fix eta t, if we choose a value that seems reasonable, then the BT matrix is known, and the only thing that's unknown is the values of the factors. So we have a regression problem where from knowledge of yt and bt, we estimate zt, and we do this every day. So for a given value of eta t, we can do cross-sectional regression at every time point, and it is effectively a fundamental factor modeling, factor model. However, if you also want to estimate eta t, so that could change every day, then a more complicated optimization has to be carried out. So I think this is one of these things that is just simpler if we do it with data. So in QRM data, there is a nice data set downloaded from the Central Bank of Canada webpage, zero coupon bond yields for 120 different times to maturity, ranging from a quarter year, a half year, out to 30 years. And effectively, 120, that is M. We have 120 different times to maturity. So S1's a quarter, SM is 30. And that's what we're going to analyze. So I think this is the right point to have a look for this one. This is chapter 9, obviously, and there is a script here called ZCB yields Nelson-Siegel. So what do we need? It's a time series. We have these yields every day over a certain period of time. We'll have a look at what we have. So it's a time series. We have it in the QRM data library, and I'm going to use a nice package called TermStruck, made in Austria, I believe. Let's have a little look at it. Sometimes it's nice just to have a look at the front page of these things, see who's responsible for it. Maybe you know. The zero coupon yield curve estimation. This is what we're going to use. TermStruck. Ferstel and Hayden and Ferstel, I think. Yeah. Okay. So maybe to begin with, just have a look at the data, just so you get a sense of the structure. We had a brief look yesterday, but now it's more relevant. So starts in 1991 in January, and then you have the yields for time to maturity, 1 quarter year, half year, 3 quarters a year, going all the way up, 3.5 years, etc., all the way to 30 years. Let's take a little episode. Let's take a very small excerpt from this. So I'm just going to take a period in 2011 for fairly arbitrary reasons. There's nothing particularly significant about this time period. And I'll multiply the yields by 100. So I'll express the yields as percentages. I'll multiply them by 100. And in this package, I have to set up the data using a function called zero yields, written by the authors of this package. So I create a little data set in the right format using zero yields, and it tells me this is a data set of zero coupon yields. Maturities range from a quarter of a year to 30 years, and it's just 100 observations just to get a feeling for what happens between August 2011 and December 2011. So the next thing is the Nelson-Siegel fit. Estim NSS fits the Nelson-Siegel model, you'll see there's an option here. So probably we can find this function and just have a little look at it. Hope you can read that. Hope that's large enough. Function for estimating the term structure of coupon bonds and yields with the spot rate function of Nelson-Siegel, Svensson, or something else called Diebold-Lee, which we'll come to shortly. So there's some optionality in the method you use. So I'm estimating it. My cursor disappeared for a little while. And then there's basically what has happened here is that a cross-sectional regression has been fitted every day over 100 days. So 100 cross-sectional regressions. You may wonder what this summary information here. You get 100 zeros because it's telling you that the optimization has converged every day. And now we look and see what we've got out of this. So I'm going to extract the results from this and plot them. I think that will be easiest to make a plot here. But these are the three Nelson-Siegel factors. So what I've called Z1, supposedly the level factor, what I've called Z2, the slope factor, and Z3, the curvature factors. And in this Nelson-Siegel method, eta is estimated every day. So you'll see the tuning parameter is varying here. In this case, it's varying in a range from 0.5 to 0.62, this tuning parameter, which begs the question, why don't we just fix it at something like 0.55 and make our lives easier in the estimation? So these are the factors, and these factors are supposed to explain the yield curve every day. So let's have a look at the quality of the fit on a particular day. For example, the first day. So this is a picture which you have in your slides. Every day, of course, you have 120 points. So you have 120 points, and the line is the fit. I've seen greater fits, I have to admit, but with the Nelson-Siegel model, this curve is the one that's been chosen to fit those points. With Svensson, you can get a bit better, because there's another factor there. You can get a little bit better. But that's essentially what is happening. And so every day there are 120 points, and every day they are described through a ZT, a level, a ZT1, a level, a ZT2, a slope, a ZT3, a curvature, and an eta. The form of the functions, just go through a few things. That's the picture you have in the... Beg your pardon? Yeah.
For typical risk management applications, I suppose, for instance, for hedging reasons or purely investment reasons, unless you're heavily in the money market, you would be more interested in fitting the long end of the curve than the short end of the curve.
That's possible, and you are looking at the deficiencies of the fit at the long end.
Right, but I suppose you could repair that by just in your data picking more data points in the long end. I suppose you penalize.
Well, that's very true, because yes, it's evenly penalized right through. So I suppose there are so many things you could think of doing if you want to, as you say, if you want to make the quality of the fit best at the long end. Yeah.
I would suppose that most people would be interested in that.
Yeah.
But I guess that's just a rather simple solution to
I guess so. I haven't really thought about it, but yes, the
regression you use to estimate the factors to penalize deviations at the long end is stronger.
yeah.
Yeah, you will explicitly go to profile using the data, of course, yeah.
Yeah, a good question. So yeah, we'll stick to the sort of plain vanilla method as Nelson-Siegel did it, but immediately sets you thinking about other things you could do to get better results. And Svensson is a bit better because it has an extra factor. So the functions that I showed you on the slide relate to that day, so that the picture in the slide relates to that day. Now, let's get a little bit more ambitious. Let's see if this works. Let's take 10 years now. Let's take 10 years of data running from 2002 to 2011. And once again, I will I will now create my data set using the zero yields. So it's same maturities, but I now have 2,488 observations running over 10 years. Obviously 10 years with approximately 250 days in each year. So what I would be doing is fitting 2,488 cross-sectional regressions. So when I press the button, I'm fitting 2,488 regressions. If I optimize the eta every day, we're going to wait a while through part of the coffee break. So I'm going to use a slightly different method. This time we hold eta fixed throughout the estimation, much quicker. And this is the option called Diebold-Lee. So this is the Diebold-Lee option. So here we have DL. Diebold and Lee wrote a paper, which is cited in our book in the references to that chapter. They've done some extensive empirical investigations, and they've come up with a value of eta that they think is good from the point of view, the statistical or econometric criterion of just good forecasting of the yield curve. It's not David Lee, it's a different Lee. It's a different Lee. And Frank Diebold, who's a well-known American econometrician. So we fit that, and it goes to work doing regression. I've lost the cursor, so it's still computing a little while. And we get something out of this. Now, hopefully this is going to work. Let's see. A new version of Quartz is available. I think, remind me later. This is effectively what it's done. And what's nice about this picture is we can swivel it round. So you get a sense of what's happened here. So in this dimension, we have the various times to maturity, going out to 30 years. And in this dimension of the cube, we have days, so 10 years, almost 2,500 days. And here we have the yields and percentages. And you can see all these curves. Generally, the upward sloping yield curve, and then something else happening. It would be better if we had dates, obviously. It'd be a bit nicer if we had dates, but maybe Marius can work on that. But in the middle, something different going on, and then we have this there. So effectively, we've captured this data through cross-sectional regressions at every time point going through here. And once again, if I now take out the factors and plot them, these are the three Nelson-Siegel factors that we get going through time, 2000. Here we do have the dates at least. So the level factor's coming down. Now we know about that. The level factor of interest rates coming down. The slope's doing interesting things. And the curvature's doing interesting things. The next piece of code shows how we can mark a significant date on all plots. I've put the 15th of September 2008 on those plots. That's Lehman Brothers. I was just curious to see what happens around that, the sort of peak of the financial crisis, peak distress in 2008. So that's Lehman Brothers. So I don't know, maybe there's a bit of a structural change there in the slopes. So that's how it works. And we've gone from, let's say in this case, suppose you had in your portfolio bonds with all of those maturities, there are 120. And so we've now gone down to dimension 3. We've gone down to 3 risk factors. And these data are now the primary risk factors to model. That's the idea. These data are now the primary risk factors. So why don't we difference them and plot them? We're now interested in these risk factor changes. And so these are now so if we want to forecast, which is what this problem of risk measurement is about, we want to work out what kind of losses could we have for this portfolio. We want to essentially take these time series and forecast them into the future. And there is evidence, it's particularly obvious for Z2, the sort of volatility in the time series of the reconstructed factors, also Z3. So maybe I won't go any further, but at this point, of course, comes in the whole statistics of Okay, so these are now the risk factors. How do we model them statistically and forecast what's going to happen? Coffee break time. So that, what you've just seen is example 9.3. Example 9.3, and the data is shown, some of the plots are shown on these slides. Now, there is another, I'll just take 2 minutes and we'll think in the coffee break about whether we present this or not, but there is probably not to cover everything we wanted to cover, but there's an alternative to the fundamental factor models, which is PCA. And what's a little bit different here is we applied the Nelson-Siegel at the level of the yields themselves. We applied the Nelson-Siegel to the yields every day. The PCA is applied at the level of the changes in yields. So you difference your yields, and you get these time series of differences. If we take the Canadian data, we'd then have 120 time series of differences in yields for the different times to maturity. And we apply a PCA factor modeling approaches to the differences in yields. And we look for factors. And once again, there's a question of how many factors. But what's quite interesting, if you take that approach and you try to statistically discover factors, you will find that generally one or two principal components, 1, 2, or 3 principal components describe most of the variation in the data. So just to jump to this point, a first principal component gets you about 87% of the variance, 2 get you to about 96, 3 get you to 97.5. This is showing you that really all of the information is contained in a very small number of principal components. And it is conventional to take 3, and when you look at the loading vectors that you get for those principal components, you find that the same interpretation of level, slope, and curvature emerges. The loadings for the first principal component suggested that it's about changes in level. The loadings for the second suggest that it's about changes in slope, and so on. It's written up in chapter 9 of the book for you to look at, but a very similar story emerges, which, of course, with principal components, you don't assume that story to begin with, you discover it. So there's a consistency in what you learn from the Nelson-Siegel approach and what you learn from the PCA approach.
Okay, so let's start again. We will talk about market risk measurement now. And this now goes back to what we had in chapter 2 a little bit. So we identified 3 key tasks of quantitative risk management. The first one was to find an adequate model for our vector of risk factor changes, then to derive in some way, explicitly, numerically, approximately, the loss distribution function, so distribution function of LT plus 1, and then from there compute risk measure estimates, value at risk expected shortfall. So those were the 3 key tasks we identified, and and at the moment we can now think a little bit what we did. So in chapter 6 we mostly thought about more interesting models than the multivariate normal for this vector of risk factor changes. We will do that again tomorrow in even more general context, and then for the loss operator, we treat as given mostly. We can look at the linearization and approximate it. There's also currently quite new research on how to approximate that in case you don't know it explicitly. We don't treat that case, but I think it's interesting to point out there's more coming up. So we have our vector of risk factor changes. We assume we know the loss operator. And then our problem is, of course, the statistical estimation of the distribution of the risk factor changes, and then the recurring or deriving from there the loss distribution function. So these are the tasks. And now Rüdiger introduced you already to the 2 different frameworks. So the loss distribution function could be unconditional. like in a stationary IID context, for example, or it could be dependent on that flow of information. Yeah? So FT, yeah? So it could be a conditional approach. Alex will do a little bit more on that soon. And yeah, so our problem in general is this conditional loss distribution function. So and here we have the loss operator in there, we have our risk factor changes in there. And if you look at the unconditional case, then simply use your pen and cross out this part here. Yeah? And then under the in the unconditional approach, essentially, you assume, let's look at the simple case. You have, for example, IID risk factor changes. Yeah? So you can replace essentially this by one random vector x, and you can drop the t there. Good, so this is that essentially. And so, okay, and something I want to point out here is that concerning the conditional approach more towards time series, there's one vignette I would like to very quickly point out. So let me just quickly switch here, because I think that very nicely puts together time series plus what you already learned on risk measures in Chapter 2. So it's quite a long vignette, but most of the things you discussed with Alex and time series already. And in the end, it's kind of just want to quickly show you one plot that more or less brings together a lot of things. So I first start by simulating a certain process, ARMA with gauge errors, and then I fit the corresponding process. I do as if I don't know the data. I fit the corresponding process. I derive from that estimates of value at risk, and then I also predict over a certain period that process. I predict value at risk, and I even get bootstrap confidence intervals. It's not the very best script. There could be many improvements in many ways. You could even do that multivariate as well, but just want to quickly point out that these things can be done. Good, so now let's move on. So what are the types of approaches we can use to solve these key tasks of risk management? And we really look at the first two at the moment. Yeah? So rather than thinking about the best risk measure estimates. So in the variance-covariance method, we assume the distribution of our vector of risk factor changes to be known. Yeah? And not only known, but to be a very specific one, namely the multivariate normal. Yeah? And in the unconditional approach, you would have simply a mean vector to estimate and a covariance matrix that fully determines the normal. And in the conditional approach, you would have the mean vector and the covariance matrix being dependent on time. Yeah? But either, like the unconditional version is definitely, if you feel uncomfortable with what this F means and so on, yeah? It's to understand the method, it's definitely fine to look at the unconditional version. The conditional version itself, like you need dynamics for the mean and the covariance matrix, and there you learned a lot from Alex already, so you could fit, for example, a multivariate ARMA gauge model, so based on multivariate normal innovations that would fit into this context. Or you can use this slightly simpler approach by an exponentially weighted moving average and specify the dynamics of your covariance matrix like that. And essentially what this is your estimate, your non-parametric estimate of the covariance matrix, but instantaneously, so just today essentially. Huh? So that's what this is, and that you use with a certain weight, and with 1 minus that weight, you use the previously computed estimates, and that gives you a dynamic. So you have the two parameters, if you like, or vectors, you can call them matrix as well, to estimate. Okay, and so in the variance-covariance method, the most crucial part is that you have a very specific model for your vector of risk factor changes, namely the multivariate normal. And then you have the loss operator on top. Typically there, because we have a very specific model, ideally we want to have specific loss distribution, and so we also assume that the loss operator has a certain form, we use the linearized loss operator in this case. Huh? And this now goes back to, if I remember correctly, it was page 19 or 20, yeah, page 20 you had on the slides. So this is our toy stock portfolio example, and the linearized loss will of course always be of this form. And so in our stock portfolio example, the CT was 0 and the BT were the certain quantity, certain weights given. But in general, your linearized loss operator will always have this form. The CT is the derivative of your mapping F with respect to time. And the BTs contain the derivatives, the first order derivatives of your mapping with respect to the D risk factor changes, or the D risk factors essentially. Yeah, and so once I have a very specific multivariate model and a very specific form of the loss operator, then I have hope to say how my linearized loss here is distributed, namely univariate normal. And this now is this important result that if you start with a multivariate normal distribution and you build linear combinations of that, so it's completely independent of risk management, if you like, then you get, in the end, a distribution that's known, namely the normal again. And now you can already say, hey, I know how to do that in a smarter way. So we discussed elliptical distributions yesterday. So you, of course, can extend that to elliptical distributions. Then you would still know that the univariate, the linearized loss operator, the linearized loss is elliptically distributed. So you can essentially extend that a little bit. Now, but the classical variance-covariance method uses the assumption of the normal. Yeah? So you have very critical here, and I love to ask this my students in the exams, what are the assumptions behind these methods we discussed, and here you have two crucial assumptions: multivariate normality for your risk factor changes, plus your linearized loss operator is a good approximation to the actual loss operator. So those are the two critical assumptions. But you need to have assumptions, otherwise you don't have any hope to say how your loss is distributed.
No, I was going to ask, this is a univariate.
Yes, that's important. Yeah, your vector of risk factor changes, that's always a vector. That's the D-dimensional case, chapter 6, chapter 7. Yeah? But once you go to the loss operator, to the loss distribution itself, that's univariate.
Yeah.
Yeah? For us, that's univariate. So this is the univariate normal here.
Yeah.
Yeah? And that's the mean and the covariance matrix of the multivariate normal for the underlying vector of risk factor changes.
When you use this for market risk, this approach, over what time scales would you use that approach, these two assumptions? Over a time scale of 1 day, a week, a year?
10 days. Alex, any comments?
Relatively short periods.
Yeah.
A day, a week, 2 weeks. These kinds of methods. Of course, in banking, it's typically daily or 2 weekly. In insurance, problem measuring risks over 1 year. So that's where things like scaling deals and aggregation come in. Yeah, so there are more methods coming up later on. Monte Carlo, probably, I don't know that this has been used in insurance, but in terms of statistical methodology, it's sort of the first one that anyone came up with.
I'm asking the question because this is the basis of the standard Swiss solvency test, market risk.
You wouldn't use it in insurance, or you shouldn't use it in insurance to compute the risk factor or the profits and losses over 1 year. You might use these things for the management of this portfolio, which you do also over shorter time and the asset guys. And it's strictly
But that's not a solvency issue.
That's not so much. I think the solvency, I would say you have to go to simulation for 1 year.
Thank you, that's what I wanted to hear.
Okay, so let's continue. So once we have specified that model, the multivariate normal for our vector of risk factor changes, and use the linearized, or agree that the linearized loss operator is a good approximation. We have the full distribution of the loss, namely a univariate normal, and then we can derive from that valued risk and expected shortfall. And essentially, you see here the mean of the univariate normal, the variance of the univariate normal, they appear here and here again. Yeah? So this is your mu plus this is the square root of the sigma squared here. So that's your standard deviation of that univariate normal. And then that's the quantile function, yeah, at alpha. And this is not special to the normal. Yeah? So this is, I think, important to mention. Any location scale transform, I think Rüdiger already did that in 2. So any location scale transform distribution will give you the same location scale transform of the corresponding quantile function of that distribution you start with. For those who are interested in, it's a one-line proof, I gave it here. Yeah? So your location scale transform a certain loss with distribution function FL. You write its distribution function in terms of the one of FL, then you set it equal to alpha, you invert it, you solve it with respect to x, and that's your value at risk, your quantile at level alpha. Yeah? So, and you see the mu plus sigma first walks to the other side, and then it walks back again exactly to that form. So you see you essentially invert it twice, and that's why you get this form. And even more general, yeah, so if you have an increasing transformation here, for example, something invertible, any transformation G, you can bring it to the other side, you can use the same trick, and you see that you invert it twice, so the corresponding value at risk would be G of the one of the original loss. A very nice exercise, do that. Those are all one-liners, and I think they help you understanding how to work with loss distributions. But the point is, we have very explicit formulas here, yeah, for expected shortfall as well. So that's of course, the best part about it. So we have an analytical solution. So the variance-covariance method is a special case of all these analytical methods that give you something explicit, but it's one of the rare ones that actually does give you something explicit. But then our disadvantages are obviously the assumptions. So the linearization might not be a good might not be a good approximation. And the assumption of multivariate normality we saw, for example, in the BMW Siemens data might not hold. No? But as I mentioned before, you can extend that to elliptical distributions as well, because they are also robust undertaking linear combinations. You stay within the same class of distributions, or at least in the known distribution. Good, so this is the variance-covariance method. And essentially what we did was we fed our loss operator, or the linearized loss operator, with a parametric model for the vector of risk factor changes. Now, as a statistician, you know there are parametric estimators and non-parametric estimators. So maybe we want to use a non-parametric estimator for the distribution of the risk factor changes. Yeah? So that can be done as well, and that's then known as historical simulation. So what you would do is you would essentially feed your loss operator or linearized loss operator with the actual realizations of the past so many, let's say, n days. Yeah? So the actual realizations of risk factor changes. And as such, it will appear later on as well. This is actually has nothing to do with random number generation in the sense of simulation. Yeah? But it has to do with simulation in terms of you simulate what happens to your current portfolio composition, so your loss operator under T today. You simulate what happens to your current portfolio if you plug in those types of losses or risk factor changes you see from the past so many days. Yeah, so you simulate what happens to your current portfolio under the types of risk factor changes you see in the past. So in that sense, simulation does make sense, yeah? But it has nothing to do with random number generation. Alex will tell you the true simulation approximation, so to speak, where you actually simulate from the xt plus 1s, yeah? From another parametric model. That's then Monte Carlo. Yeah? Good. So if I use my past risk factor changes, what type of assumption do I have underlying? And many students get this wrong. They say there's no underlying assumption about, let's say, the dependence between my risk factor changes. But that's actually not true. The underlying assumption is that my risk factor changes follow the corresponding empirical distribution function. And that multivariate empirical distribution function of these risk factor changes, that has a certain dependence between the components. Yeah? So there is this assumption that my risk factor changes in the future evolve according to that dependence, for example. Yeah? So there is kind of an implicit assumption, but of course I do not specify explicit a parametric model here, which makes this method very nice to apply because I don't have to know anything about fitting, I don't have to know anything about multivariate distributions. All I need to do is I need to collect these losses essentially. But there I have another problem because if that's high dimensional, yeah, then I might not be able to observe all the components of X at every time point. Yeah? And that's, of course, a bit of a problem how you deal with that. And that problem, that's then, actually, we will come back to that tomorrow in chapter 8. Yeah? So you could also say, well, these risk factor changes evolve in very different ways. I do not observe them simultaneously. They have no obvious connection, so I could actually model the two subvectors, if you like, separately, the two losses separately with these approaches, and then later on think about how to combine the two loss estimates I have. Yeah? So that can be done as well. But don't worry, it's a bit much at the moment. That will come back tomorrow in chapter 8. Good, but yeah, so I will, and then the losses I construct from here are, of course, those past risk factor changes I plug in, I compute the loss operator, and those are the losses I then use, essentially. Now here I typically, but you still can, I typically do not use the linearized loss operator because there's little hope to get the distribution of my losses explicitly anyways, so I typically do not do another approximation here. Yeah? But then, of course, what I could do, there are also different versions available. I could fit to these derived losses a parametric model, yeah, or I could use the empirical distribution function, now a univariate empirical distribution function, to derive risk measure estimates like value at risk and expected shortfall empirically like we did now. Yeah? So there are different options here available as well. Again, typically you would use non-parametric estimators of the risk measures as well. Good. So what are the advantages and drawbacks? So typically, if you use an empirical quantile estimate, let's say for value at risk, then of course the question is concerning precision. I don't go in detail here. We discussed that in R. You saw the two risk measures for the Pareto, and you saw that our value at risk and expected shortfall estimates cut off, so that we've seen. But then, as I just said, you can also fit parametric model. Then, of course, the next question is which parametric model? But still, the good part is you are at that stage already in the univariate setup. Yeah? So you have a lot of tools available, a lot of distributions, goodness of fit testing, and so on. Yeah? Or you say, okay, the bulk of the data, given I have enough, I model with the empirical distribution function, so the bulk of these univariate losses. And in the tail, I use one of these value at risk expected shortfall estimators based on the GPD approximation. Yeah? I also have something like that in R, but I'll show that to you later. But that's what you discussed in chapter 5, in the very end. Yeah? So you have the tail estimator, yeah, and based on GPD, and you can simply invert that. If you have a sufficiently large confidence interval, then your F is a GPD, essentially. You invert that, you invert the form of the GPD, you get the GPD-based value at risk and expected shortfall estimators. That's typically a good way to do it. That works very well. The theoretical justification for this method, why shall I use the empirical distribution function, why do I want to treat that problem non-parametrically, is known as the Klibenko-Cantelli theorem, which tells you that the empirical distribution function converges uniformly to the true underlying distribution function of the vector of risk factor changes, which we don't know, of course. Yeah? So if I have enough data, then that method might make sense. So pros and cons, as before, for variance-covariance method. So here, that's easy to implement. As I said, we don't need to know anything about statistical estimation. We just use the empirical distribution function. But we need sufficient data. Yeah? If I have just 3 data points, then the last jump of my empirical distribution function is by 1/3. So for already moderate confidence levels, I will always get just a large loss. It's not a very good estimator. So I need a lot of data actually. Yeah? And then also, since I plug in my loss operator only past losses, then I assume that what's coming in the future, because I want to compute risk measures for the next period, right? The amount of capital to put aside for the next period. That's of course based on the assumption that the next period is not much different from what was in the past, what was happening in the past. Yeah? And when Paul teaches that part, he typically refers to it. It's a bit like driving a car by only looking into the back mirror. Rüdiger mentioned that yesterday as well. I think it's a very nice analogy. Be careful. In one of the exams, one of my students wrote, it's like driving a car in the back mirror. That's a slightly different thing. Yeah? So be careful to get that right. Good. And as I mentioned before, there is underlying an assumption about the dependence actually. Yeah? It's not a parametric one, but the assumption is implicitly contained in the empirical distribution function of your vector of risk factor changes. So there is an assumption underlying essentially. Good. Yeah, so Alex? I think, yeah. So I show you these methods later on in R. Alex will do the more dynamical part now, and will also discuss Monte Carlo methods, and then that will be contained in the R script.
Okay, so you've probably seen that this section of the book, this section of the workshop, it has a little bit of a bank bias. This methodology and the 3 methods that we're going to treat, variance covariance as mentioned, historical simulation, and Monte Carlo, this idea of 3 methods kind of comes from banking and Basel. And in insurance, the question is, I suppose, which of these methods are useful in the insurance context where time horizons are a little bit longer. Historical simulation is incredibly important in banking, or incredibly popular in banking, popular method. There was a survey paper came out a couple of years ago looking at banks, what methods they used. About 70% use historical simulation. But some of them do it in a slightly more sophisticated way than others. So volatility is really important over short time horizons, 1 day, 2 weeks, 1 month. Whether it's important over 1 year, it's less important, but it's important over short time periods. So the banks have methods which you can call filtered historical simulation. I download it because now under Basel you have to disclose your VAR measures, so you can actually find on the internet, you can find documents produced by banks where they divulge their methodology to some extent, and so you'll find that you'll find reports where they say they use dynamic or filtered historical simulation. So in 9.2.4, I'll give a sense of what dynamic historical simulation is. Firstly, a simple approach, which in fact no banks use, but we may, depending on how time goes, we may illustrate this with R, or we may not, but first a simple approach, and then secondly the approach which I think most banks who use a dynamic approach would use. But I think that of the banks that use historical simulation, probably less than half use a filtered approach, and many of them use the plain vanilla method that Marius has explained. So, in historical simulation, we pass historical risk factor data through the loss operator, or possibly through a linear or quadratic version. When you have very complicated portfolios with exotic products, of course, you may use the approximations rather than do full revaluation, which is time-consuming. Why a tilde on the L? The notation in this book, we thought about it quite carefully and argued about it at length, but these are never observed, these L tildes. They are what-if scenarios, because we have observed the excesses, they really happened, but LT is today's portfolio, and so L tilde S, the historically simulated loss. It's never been observed in the past. It's what would happen if historical changes were applied to today's portfolio. But we can create a time series. We can create a time series L tilde, and a very simple thing to do would be just to model this time series. So this is a univariate approach, very simple-minded. Model this time series and predict the next value, or model the distribution of the next value and compute quantiles, expected shortfalls, other risk measures. So this would be the task. Now, LT plus 1, it doesn't have a tilde because this is what will actually be observed. The loss that is created by the risk factor changes that will happen in the next time period. So this is, we want to predict, we want to predict this random variable or predict risk measures which describe the distribution of this random variable. So we have this sort of model that we talked about at length on Monday and a little bit yesterday afternoon, but in fact we looked at the multivariate case. So there might be some conditional mean model, ARMA, and there would certainly be some modeling of the volatility, and we would assume that we can model the mean, we can model the volatility, and there is an innovation distribution ZS, strict white noise, with some distribution FZ. So, for example, Gauge model with ARMA mean structure. Now, these general formulas for value at risk that Marius has given the idea of where they come from, in the Gauge context, we would get similar formulas. The value at risk for the loss LT plus 1 at level alpha, it would be given by mu t plus 1, the conditional mean, time t plus 1, plus the volatility at time t plus 1, times the alpha quantile or the alpha value at risk of the innovation distribution. And the same thing for expected shortfall. So these would be the kind of formulas that we would use to determine VAR, but of course we need to estimate mu t plus 1. We need to estimate, that's a less important feature, but we would certainly need to estimate sigma t plus 1, and we would need to estimate or calculate risk measures applied to the innovation distribution. So here are just some options. We can do the formal time series modeling. We can fit, for example, an ARMA Gauge, an ARMA 1-1, Gauge 1-1 with student T innovations, or perhaps skewed student T innovations. That might be nice. And we could get everything. We would get an estimate of mu t plus 1, an estimate of sigma t plus 1, and we would immediately from the estimation get the parameters of the distribution of Z, and from those we could determine the value at risk and the expected shortfall. Or what's very popular in practice is always to use these exponential schemes because no estimation is necessary with these exponentially weighted moving average schemes. Generally, someone who uses this just sets the conditional mean to be 0 and neglects it and applies a volatility filter to predict sigma t plus 1. And then how do you get quantiles and expected shortfalls for the innovation distribution? Well, you would effectively get a series of estimates of volatility. You would compute residuals, that is, you would divide the historically simulated losses by the volatility estimates, and then from these data you would do some quantile estimation, some expected shortfall estimation. So those would be two options. But as in the case of standard historical simulation, so going back to what Marius said, what's the best place to look at that? Yeah, you always have, or you would have, if you took the second approach with exponentially weighted moving average, you would have these options. Do you do empirical quantile estimation, but applied to the residuals? Do you do something parametric? Do you perhaps use the extreme value methods? So again, you would have these options, but the difference is that it would be applied to the residuals. If you like, it would be applied to the innovation distribution of Z. So That's a simple-minded thing to do. And in the repository, there's a script which does that kind of thing. So we might run that. We'll see how time goes. We might run that script. What the banks who do this are likely to do is something more sophisticated, a multivariate approach. And this approach, it dates back to 2 papers, one written by Hull and White, and another written by Baroni and Daisy, and I think a couple of co-authors who suggested, we call it a multivariate dynamic historical simulation. I will try and give the idea of it. So we have, in this case, we have d-dimensional risk factor change data, and we assume it follows a multivariate time series model of this form. So we have perhaps a conditional mean term, but of course this part is the less important part. We have a volatility matrix. Remember, this was the notation from yesterday. When I briefly talked about multivariate gauge, I had a delta T matrix, which was the matrix of volatilities for each of the risk factors. So that's what this says here. It's a matrix, a diagonal matrix, D by D, but nothing off the diagonal. On the diagonal, you have the volatilities for the D risk factors at time S. And ZS here will assume that this is strict white noise. So this is strict white noise. What does that mean? It's a fancy way of saying independent, identically distributed with some distribution which we would assume it has mean 0, and we would assume it has some correlation matrix P or rho. So mu S contains the conditional means, delta S contains the volatilities. We've seen a model that fits exactly into this framework, CCC gauge. The constant conditional correlation gauge model fits into this framework. And as with the univariate approach, the idea is to try to apply historical simulation at the level of the innovations rather than at the level of the data. So these methods, that's the intuition. You try and historically simulate the innovations, the news or the noise, rather than the data. But of course, the innovations are never observed. You have to filter them out with a time series model in order to apply this approach. So I've written this down step by step. You have some model. You use this to estimate the conditional means, less important, but importantly, you use it to estimate the volatilities for each of these time series. So this is matrix valued. And what is typically done in practice is just fitting univariate models. Although I've written this down as a multivariate model, what happens in practice is typically you fit univariate time series models of gauge type to each of the component series, or you can apply the univariate exponentially weighted moving average to each time series. And then having done that, you've effectively estimated your volatilities, so you devolatize. This operation is devolatilization. This is the filtering, where you filter out the volatility and you create some residuals, which you regard as observations of these unobserved innovations. And then comes this step here, where you feed these residuals, these reconstructed innovations, beg your pardon, you feed these into the loss operator. You pass these vectors here into the loss operator, and you get some historically simulated losses. But these are now dynamically historically simulated losses. You treat these as observations from the distribution that interests you, and you then have some options, again, as to how you actually compute VAR, how you compute expected shortfall. You can apply simple empirical estimators. You can apply parametric estimators. But you create this data set, and once again, this is a univariate data set, and you work with this. So that's typically what a sophisticated investment bank does, the methodology. I'm not sure how many of them bother to do the GARCH, how many of them do the exponentially weighted moving average, but it will be a procedure along these lines that they will call, sorry.
Where this delta hat T plus 1 come from?
Oh, okay, so where does that come from? So you've got all of these. This comes from basically forecasting the next value because you use the GARCH or you use the EWMA to forecast the next value. That's a good point. So so you've got to forecast the next value of that, and you've got to forecast the next value of that. But you have the equations, either the GARCH equations or the EWMA equations. Yeah, good point. So it's explained in a little bit more detail in the book. There's a third generic method that people talk about. And so in this survey of what banks do, 70% use some form of historical simulation. The rest probably use a Monte Carlo approach. I think the number that use variance covariance is very, very small. The rest probably use Monte Carlo, and Monte Carlo is very, very general. It's like a family of methods, but here the idea is that you want to estimate the distribution of the loss under some very explicit model for xt plus 1, something that you can simulate. So you don't pick the multivariate normal because it's tractable, or you don't pick the multivariate student because it's tractable. You don't do resampling, but you pick a model that you like. You pick a fully specified model that you think is a good model for the risk factors. So I think I've said this. In contrast to variance covariance, you don't try and make your life easier by linearizing and by assuming normality. And here it's genuinely Monte Carlo in the sense of random sampling. Historical simulation, as Marius indicated, it's a misnomer because there's no Monte Carlo random number generation in historical simulation. It's just passing past events through replication. It's actually bootstrap without replacement is another way of describing it. But this would be true Monte Carlo. You have a model that you can generate from. Now, in insurance, you might call this economic scenario generation. So you might have an economic scenario generator, some complicated model that allows you to generate scenarios for the way that all your risk factors change. So equities and interest rates, exchange rates, whatever financial variables you need to value what's in your portfolio or to value your assets and potentially your liabilities. So economic scenario generation fits under this heading. And this is something that I've looked at a little bit. Being in Edinburgh, I was in the same city as the former Barry and Hibbert, who build economic scenario generators. So I've spoken with them at length. They are now part of Moody's Analytics, incidentally. So it's simulating new risk factor data. So you find a model for these risk factor changes. The way I've written it here, it suggests we find a time series model, a discrete model, but it could be some continuous time model, which is what, for example, the Barry and Hibbert economic scenario generator is, from which you can generate changes over the time interval that interests you, whether 1 day, 2 weeks, 1 month, etc. So you pick a model and you generate you generate risk factor changes for the time period t to t plus 1. Let's say two weeks into the future or 1 month into the future, and you do this as many times as you want. So n here is a large number. Because it's proper random number generation, you pick the n that you can handle, as opposed to historical simulation where you're constrained by the amount of historical data you have. And you generate these n scenarios, and then you pass them through the loss operator, or the linear loss operator, or the quadratic loss operator, and you get the losses. And then you're right back in the same position where you have a set of numbers, univariate, and you have some options for estimating quantiles and expected shortfalls. So you can do the empirical quantile estimation, you can do the parametric quantile estimation, you can do the EVT. So I suppose the pro here is this is very, very general. You pick any distribution or any model you want and which you find plausible and economically realistic. And that's also the disadvantage because this is, what do you take? This involves a bit of effort. Could be time consuming if the loss operator is difficult to evaluate, but of course you can, in banks typically they do use delta gamma. They don't fully revalue all their positions. They do it quickly through delta gamma. Monte Carlo doesn't address the problem of determining this distribution. It's just very genetic. So you've got a lot of work to do in building the model to simulate xt plus 1. But I suppose that's what these vendors are doing, who build economic scenario generators. There are 2 slides here in section, actually 3 slides in section 9.2.6.
Just to
Yeah.
to get back to the previous one, just determining the distribution of xt plus 1, I mean, this is the fundamental, I mean, that's the base,
Yeah.
the building block.
That's a building block.
So basically you would do that maybe on some fundamental things like an interest rate or something, not on a principal component. Or would you do that also on a principal component?
Well, so I think the dimension reduction may be in here. So you have the risk factors that you find important. So your model with which you generate xt plus 1 may involve some dimension reduction. You may have decided to boil the term structure down to 3 factors, for example. You may have decided to boil or to reduce the world of equities down to just modeling major indices. So I think I would say there's some dimension reduction involved already in the choice of what are the risk factors.
Okay, but I was thinking not a principal component derived from a principal component analysis, as what you did yesterday, where you didn't really know what's actually in there. The first one, remember, was an index. The other one was the difference between technology and non-technology.
Yeah.
Or would you still do that with a...
Well, it's completely general. It could be. So components of this could be principal, elements of this vector could be principal components. But then we'd need a model for how these principal components change if we're then going to use them to explain the losses in the portfolio. So
Principally, you could look at their historical
Yeah.
values and then...
Yeah, once you've constructed time series of principal components, you can treat them like historical data as well. And I didn't run that script, but if you play around with the script in the repository that says PCA for the yield curve, zero coupon bond PCA, you construct those time series and you look at them and you see that they show a bit of stochastic volatility, and you could fit some models to those as well. Yeah. So I'm not going to say too much about this section because it's really just a summary of estimation methods. Whether you do historical simulation or Monte Carlo, and whether you do the historical simulation statically or dynamically, in most of these options, apart from the parametric one, you end up with a set of numbers and the task of estimating a quantile from a set of numbers or an expected shortfall. And basically in the book, we never really look beyond 2 methods in that situation. Simple estimators based on order statistics or based on the empirical distribution function, and methods based on extreme value theory. So L estimators, these are estimators based on sample order statistics, which is just you have your sample of losses and you order them, and you compute the estimators from those ordered values. Or the GPD methods that Paul and Marius talked about yesterday morning. With value at risk, the simplest L estimator, you obtain that by effectively computing the quantile of the empirical distribution function. You compute the quantile of the empirical distribution function, and you get an estimator which is a particular order statistic. If you've never seen this notation here before, it's the ceiling function. the smallest integer greater or equal to n alpha. So this would give you a particular order statistic. And that's why technically it's an L estimator. If in R, you tend to take averages of two order statistics rather than just taking a single order statistic. For expected shortfall, you can have the natural way of estimating expected shortfall empirically, which Marius illustrated in a script, involves, again, can be written again in terms of order statistics. And then also for summary, I've just written down again the two GPD estimators that we can use if we use the POT, the peaks over threshold. So the intention now is to try and put some of this into action. And for that, Marius is going to do that. One idea that will emerge as we do this is the idea that we should backtest a procedure. Once we've made these estimates, then you can see what happens, and this naturally introduces the idea that you backtest the procedure. So we'll come back to 9.3 after we've tried to do some statistics.
Switch the display. Okay, so this is a very nice R script, quite one of the older ones, I'd say, about applying certain methods we discussed, variance, covariance, Monte Carlo, also EVT-based methods, historical simulation method for estimating valued risk and expected shortfall. This is based on the BMW Siemens data, not the classical one you've seen on the pictures before, but in the 10 years from 2000 to 2010, and that's in QRM data. So formerly the old data set was not easily available. So yeah, that's very nice. So you just have some packages to load here. Now, we need a package for, well, we actually don't, right? We don't need a package for sampling from the multivariate T. We know how this works. Just for convenience, to make it like a bit more compact, more readable, I use a package to do that. And then also for fitting the multivariate T and the GPD distribution, I use a package. And yeah, good. So let's load the data and pick out the time period we work with. That's something Alex showed you yesterday a couple of times. We can look at the beginning of the data, the end. Towards the end, you see there's some data missing, and that missing data are, of course, the holidays, the Christmas holidays. And okay, so just use that. Oh, here it is. It's a bit better visible. Okay, yeah, so, and of course I have to treat the missing data here. I use a very simple method. I fill the NAs with the NA fill function, which is a very nice function, has quite some different methods available as well, and you know how to study that now. Look up the help file, and I just pick out the two time series, BMW and Siemens. And then it's always good to start with a plot. I want to see how does my data look like? Is there any strange effect in there? So I want to see a little bit of the data here. So that's the Siemens stock. That looks all pretty fine. I compute the log returns, and I plot them. So you see that looks very similar to the types of data we've seen yesterday. Now, here I need to write something. So this is based on example 2.2 in chapter 2, page 19 and 20. So that's our baby example of the standard stock portfolio. And yeah, so that's the corresponding loss operator here now as a function in the matrix of risk factor changes. So not a vector. In R, I want to work with objects, whole matrices, right? I have several observations of factors, essentially. So therefore, I have an n by d matrix. And I have the vector of weights. And yeah, and then it's, this is a really nice line to study. So it's a bit of beauty of R here, what you can do. You have the x minus e to the x minus 1 function in a numerically robust way here. So 1 minus e to the x appears in the loss operator, so that's why I have minus here. And then I essentially multiply the weights, so I have the vector of weights a couple of times in the matrix, and then I can multiply that matrix to the matrix of risk factor changes. I built the row sums, and that's essentially the loss operator. So very good exercise for you. Study this line and compare it with exactly the slides you have, the loss operator on the slide. Make sure you can do that transition from the mathematical notation to R. It's a very good exercise to do. Good, so to be careful here to fill the matrix row-wise, for example, so I use the by row equal to true here. Good, and then I want to compare all these methods. And in R is really about writing functions. Everything in R is either a function or an object. So I want to work with objects and I want to apply functions to that object. And that's quite different from, let's say, C or C++, where I create a vector, allocate a vector, and then I run through one element at a time. No, I want to study that whole object at a time and apply functions to it. No? And here my function is simply called risk measure. I give it an n by d matrix of the original stock data. The lambdas is the vector of shares in each stock, and that's also used in the slides notation as mathematically the lambda. Alpha is, of course, my confidence level. And then I have various methods here: variance, covariance, historical simulation, the Monte Carlo. There I have to specify a model based on the normal, Monte Carlo based on the t, and the GPD approximation, EVT-based approach. And of course, you could add more here with the dynamic version as well. That would actually be very nice. Good, a little bit of input checking here in such an important function. And then I determine which method is used. And now I apply, I compute the log returns. That's what's happening here, essentially. And I grab out the last row of my stock values. Those are the last available ones are the ones today, right? So those are the S sub t's that come into play as well. And then my weights, also to know the W on the slides, are actually just lambda times ST. So this is that part. And then I then I consider the different methods. So what do I need for the variance covariance method? The underlying assumption was the multivariate normal. So I want to choose the best multivariate normal I can. So I need to estimate the mean vector and the covariance matrix of my vector of risk factor changes. Those are these two lines here. And then I know that my linearized loss operator on top will give me a univariate normal. And so my linearized loss operator, L delta mean, so this normal distribution has that mean and that standard deviation. And again, compared with the slides, you even see that the notation is similar, so square root of W transpose sigma head W. And then all I have left to do is I need the quantile of the normal, so this part here. And so I simply have that. And then value at risk and expected shortfall, I can compute and return. Those are exactly the formulas. Yeah, mu plus sigma times value at risk of my underlying standard normal, and that's the formula for expected shortfall. Now, the historical simulation uses the loss operator itself. So here I need my function loss operator. And you see how quickly I can do that, and just essentially in 2 lines. I could even do it in 1 if required. Yeah? So one loss operator is 1 line, that's essentially 1 line. So it's very easy to compute. I feed my loss operator with the risk factor changes I derived from those past losses or past stock values I passed to this function, with the corresponding weights in the portfolio. So this is very easy to derive the losses, and from there I simply use my non-parametric value at risk and expected shortfall estimators, which we also already discussed in the first R script we studied. And then for the Monte Carlo method, I actually need a sample size as well, right? Because I need to simulate. Now, since I only need that for the Monte Carlo method, I pass this on to this bigger function through the ... arguments. So that's very helpful if you haven't seen this before. So I can pass that on. So the first thing I do is I check whether I have n specified, and then I grab that out of the ... argument. So I have my sample size, and then I just estimate my mean vector and covariance matrix. You see it's exactly the same as before for the variance-covariance method. And then I simulate, in this case where I specify the normal as my model, I simulate from that fitted multivariate normal capital N many times. And as Alex hinted at before, this is of course a bit ridiculous to use the Monte Carlo based on the normal, but I want to compare these approaches. So because I really don't know which one is the best, and typically a good approach is to implement several methods and see if they give the same results. If they roughly give the same results, then I can sleep well. And if not, if they give significantly different results, I should be worried. Is it a computational problem, numerical problem? Is it a theoretical problem? So that's important. Good, and then once I've simulated my losses, I do exactly the same as in the historical method, but instead of feeding with the historical losses, I feed, of course, with the simulated losses. So I feed my loss operator, compute my weight. So I think the nice part here is you really see what's done one step at a time and how easy it actually is to do if you have some of the building blocks like your loss operator, for example. You also easily see how the methods compare. So Monte Carlo has aspects of variance-covariance method and historical simulation method, at least in the code here. Good, so I have my losses, and then I use, for example, here also the non-parametric estimators. I might in the end be interested in what actually was the fitted mean and covariance. So I pass these on as well. So yeah. And then I do exactly the same for a different model here for the T. So exactly the same code. There I also might be interested in, I fit the multivariate T here. So I might be interested in the corresponding degrees of freedom. So I also pass them on. Good, and then the GPD-based estimator, this is now going to chapter 5. So I compute here, in this case, my loss operator based on the historical losses, or the historical risk factor changes. And then I fit a parametric model to these losses, or actually semi-parametric, in the sense that I say, to the excess distribution over a sufficiently high threshold, I assume by Pican-Spalke-Madehan, this is GPD, so I assume I know the tail, I invert that to get value at risk and expected shortfall. So the way this works is I specify a quantile in this case, I pick out all losses that exceed that quantile, we've discussed this in detail yesterday, and then I fit a GPD to these exceedances over this specified threshold. And then I can extract the fitted psi shape parameter and fitted beta, the scale parameter, and I can put in a check whether my psi indeed was positive. As Paul always tells me, it should be positive, so I want to check that here. And then I can extract the excesses over U, because that's computed. I don't want to waste that. I want to return that and study it later. So I grab out among the exceedances all those that exceed, among all losses, those that exceed U, and then I subtract U to get the excesses over U. So those are the computed excesses, and then those 3 lines are the computed value at risk and expected shortfall estimators based on this GPD approximation. And then I return this information, so value at risk, expected shortfall estimators, I compute it, but then also this additional information, what was exactly the fitted GPD distribution? Did that fit converge, that optimization? Then what was the threshold that was used? And the actual excesses over U. Because I want to do a little bit of goodness of fit testing and checking whether my excesses indeed come from a GPD distribution. So this is all contained in this function, so let's do that now. I specify some numbers here, so 10 shells in BMW, 1 in BMW, 10 in Siemens. Confidence level, I use 99% here. Monte Carlo sample size 10,000. Obviously, you can change all these numbers. I set the seed to make this reproducible, and then I compute all of these risk measures estimates, and you see that's all very quickly, and then I can just pick them out in a nicer way, and typically it's nice to sort them in increasing order. You see increasing order in value at risk also implies increasing order in expected shortfall, so that's very nice. And obviously I immediately see value at risk is smaller than expected shortfall. That also makes sense. But in the end of the day, and you heard me saying this a couple of times, but I really want to stress that in the end of the day, I want to look at graphs. I want to see if the behavior is right. And you could look at 1,000 of graphs here, but I just want to quickly look at the GPD-based estimators. So I grab out the return excesses, my fitted parameters psi and beta. The monotonicity of value at risk with respect to the different methods, that we will, I just do that, I just sort the methods accordingly because I think it's nicer for the comparison in the end, but we will get there. There's no apparent, typically you see more if you sort data, but yeah, that's really a minor detail here, it's not important at all. Good, so I grab out the excesses, I grab out my fitted GPD parameters, and then Rüdiger discussed the result, and you see how nicely we can combine all of these results now. So we learned how to simulate from the normal with the quantile transformation that we also needed to study copulas. The other direction is, so to say, if I have a random variable that follows a certain distribution function f, then f applied to x follows a uniform. So I can use that, the converse, namely going from some distribution function to the uniform, the probability integral transformation, I can use that for goodness of fit testing. If I use my fitted GPD distribution here and I apply it to the excesses, and the excesses should, if I've computed the excesses over a sufficiently high threshold, they should follow the GPD, then I should get a uniform. So why don't we look at that and see if the data is indeed uniform? Now, the human eye has a very good intuition about uniformity, so I can simply look at the data, and that looks pretty uniform already, but of course I can do a slightly more sophisticated a QQ plot, and that looks pretty nice too. So you can extract the excesses, apply your fitted GPD distribution to them, and just check, do that visually, check and learn from the data. But of course this was not what we are after, I just wanted to show that you can do a little bit of checking here. What we are after is this plot here, so that now plots all the results essentially, all the losses greater than 0 at least as a histogram, and then the corresponding estimators we computed, or estimates, numerically, we computed. And you see a lot of different things here. So first of all, for each of these types of lines, you have them twice. The smaller one is always value at risk, and the larger one is expected shortfall. And then you see the variance-covariance method, the dashed line, that's the value at risk estimate, that's the expected shortfall estimate. And you see the values I get are very close, and now I come back to your question concerning the sorting, are very close to what the Monte Carlo method gives me based on the normal distribution. Now I can sleep well because that makes sense. Because they are based on similar assumptions. They are based on the underlying assumption that my multivariate vector of risk factor changes comes from the multivariate normal distribution. Similar assumptions, I get similar results. I'm happy about that. But then if I look at the historical simulation method, so the solid line, then you see I get larger risk measure estimates. So that hints at the fact that my multivariate normal distribution indeed underestimated the risk. So I don't reach out as far as the true risk factor changes, the realized risk factor changes show me. So the historical simulation gives me, especially for expected shortfall, quite larger values. So that's something to worry. These two methods might not be most adequate ones. Then the GPD-based estimator actually gives me something very close to the historical simulation method. That's very nice. Monte Carlo based on the student distribution and the T, I reach out far further in the tail Yeah, so that gives me larger values as well. Valued risk is close to what the historical simulation gives me. For expected shortfall, I'm a bit larger, but yeah, you see.
That's a big difference if we change the underlying distribution, the T.
Of course. I mean, we are talking, and we do that more tomorrow. We are actually starting, or we did that in chapter 6 as well, we are starting to think about engineering. Yeah? Of course, if you give me the task to engineer a distribution, to build a distribution between the multivariate normal and multivariate T, such that I get exactly the same results as the historical simulation method, it's actually something I've never thought about, but yeah, that might be doable as well. Yeah, so you can adjust the tail. You should probably not do that, but yeah, you can play around with it. Yeah, and I see you enjoy doing that, so that's a good thing. Okay, this is that part, and Alex tells you more about backtesting now.
Okay, so to finish, so if you've implemented a number of statistical methods, the question is what works well in practice. So that's where backtesting comes in. I think I'll try running another script to talk a little bit about backtesting. Let's change over the projectors. Okay. So you've implemented various methods. So what's backtesting? Probably it's sort of obvious what backtesting is. You make ex ante, before the event, forecast of a risk measure, value at risk expected shortfall, and then at some point there is a realized profit, a realized loss on the portfolio, and you're able to compare what actually happens with your estimate. Now, of course, if your time horizon is 1 year, you have to wait a long time till you have a lot of information to backtest an annual model. So what I talk about here is, again, really very much the way that it's looked at in banking, where this is a daily exercise, and risk measures are computed on a daily basis, both for a 24-hour and a 10 and a 2-week horizon. So you quickly accumulate quite a lot of data on how well your methods perform, and you can do the backtesting. Okay, so let's remove that picture. Didn't like that. Okay, let's try this one here. There is actually this one. There is a script actually called backtesting.r, which I'm just going to run through a few things here. And also it gives me a chance to show some other data. I'll use RU Gauge. I'm using that quite a lot because I quite like it as a package. And I'm taking SP500 data, and I'm taking VIX data here because this will also sort of reinforce some of the ideas that Rüdiger talked about this morning. So let's look at 2 time series. We have returns on the S&P 500 starting in 1990. So this diff log gives me log returns on the S&P 500. I'm diff logging the VIX. So these are log returns of the VIX volatility index, which of course relates to, it's an index of applied volatility for options on the S&P. And I have here time series of length 6,500. I will put them together. I may look at weekly returns as well as daily. So what do I have here? Plot x.d. Oh, that should be plot.zoo, I think. Yeah, so I've got 2 things here. The Standard & Poor's index returns and VIX index log returns as well. They have, we can look at the scatter plot. So one against the other, that's daily changes. That is weekly changes. Incidentally, these data always show this, a forked tail. You get an interesting forked tail when you look at X VIX and X Standard & Poor's.
So that's the risk factor data we have. And this is the situation we will think of if I just color in this block of text here. So we'll take an odd portfolio. A bank is short a put option with certain characteristics, a strike, a current value. So this specifies the current situation. Let's say the value of the index is at 80. It's in the money, and we have certain values for R, sigma, and T. So this is just a really simplistic situation, but that specifies the portfolio. And what I effectively do in the next block of code is I historically simulate the losses. So I need to value the short put option at this point. That's VT, trying to correspond to the notation. That's VT. And then I think I'll just probably look at, well, I've done it for daily and weekly. VT plus 1 is revaluing this portfolio, this simple portfolio, under the possible changes in the level of the index and under possible changes in the level of volatility. So basically, I'm passing these changes through the portfolio. This is historical simulation. And this sequence of calculations, if you read the green comment, I create a time series of historically simulated losses. Well, I'll do the gains, and there's a reason for this. When I run RU-Garch, RU-Garch has some nice VAR estimates, but it applies it, unfortunately, it uses the opposite convention to the one that we do. It models the left tail of the gains as opposed to the right tail of the losses. But that's a detail, obviously. So that's the historically simulated gains. So if I pass all these bivariate movements of the index and the volatility through my option position, now I get scenarios where the value of the option goes up and scenarios where the value of the option goes down. That's the idea. Are these changes normal? Not at all. So they're daily, not at all normal. Even the weekly ones, are they normal? Not at all normal. Moreover, they bear all the hallmarks of stochastic volatility. Interesting things going on there outside the confidence interval, but still a relatively boring picture. But look at the absolute values, lots of correlation. So this is what I'm going to do, and then I'm going to set it off, and I'm going to put it sort of in the cooker and then come back to it, as it were. You'll see me specifying some Garch models, and probably only have time to do the first one. Spec.n. So I am a modeler in a bank, and I decide to use a dynamic approach based on Garch modeling to model the VAR of my little portfolio here. So I'm going to use a dynamic approach, not historical simulation, but a dynamic parametric approach based on Garch modeling. So I'm going to fit a Garch model. I'm going to use a normal distribution because I don't know about heavy tails, so I'm going to pretend I don't know about heavy tails and use a normal distribution. But I have a colleague who knows more about heavy tails, and so that my colleague might use a specification with a T distribution. So this is what I now do. So what we're going to do is we're going to carry out a series of rolling out of sample VAR predictions. So what happens is I've got the time series and I fit the Garch model. I use it to predict VAR, and then I can see what happens. I've got the next data point so I can see what happens. And I keep doing that. I roll through time. I only refit every 10 days. So there is a function called uGarch roll, which does this rolling Garch estimation. So you roll through time, and at every point, the window size is 1,000. So it's quite a lot of data, but the last 4 years are used. As you go through time, the last 4 years are used to fit the model. And what you can't quite see here, the refit equals 10 days. And there's some other details here. So let me let me set that going. So you'll see that I've lost the cursor here. It takes a little while to fit all these gauge models. My computer here is a little bit puny, needs replacing when I can, at some point quite soon. So let me talk a little bit about backtesting, then go back to that. Because what mostly happens in banks, they are fixated at the moment on VAR, but that will change. Under the review of the trading book, the risk measure on which capital will be based will change to expected shortfall at the 97.5% level. Expected shortfall at the 97.5% level. But the approval process for internal models, even under the review of the trading book or Basel III, will be based on VAR exceptions. So although their capital is going to be based on expected shortfall, to be approved for an internal model, they're going to have to check their VAR estimates and how often the VAR is exceeded. So they're going to have to check what are called, nowadays they call them exceptions, but in our book we called them violations, but it's the same idea. So VAR is the quantile of the conditional loss distribution, and this is the indicator that the loss at time t plus 1 exceeds the alpha quantile of the conditional loss distribution. Now to begin with, I haven't put a hat on VAR. We'll assume this is the true VAR, okay? So this is the true quantile of the conditional loss distribution. This is a 0 or a 1. So this event is the exception event. If the loss is bigger than the quantile, that's an exception at the 99% level, let's say. And of course, this happens with probability 1 minus alpha. If this is the true quantile, the probability that this is 1 minus alpha, the probability of an exception. This is 1 minus alpha. Moreover, in fact, the indicators form an IID Bernoulli sequence. They form an IID sequence of 0, 1 events, each with probability 1 minus alpha. And so we can make certain inferences from that. We can infer that the total number of violations, let's say we backtest for M periods, M days, let's say. Maybe we in my example, it'll be several thousand. So we backtest over several days or a long period, and the number of exceptions should be binomial. The sum of Bernoulli's should be binomial. Other things are true. Because these exceptions are independent, the spacings between them should be geometric. I've written it down notationally, but if you look at the number of days between exceptions, I call these the spacings, these should form an independent, geometrically distributed sample with a certain mean. So these things are testable. If M is big enough, then these two properties are testable in empirical data. Forget about the last comment. Forget about the first couple of comments here. Now, in practice, of course, we estimate VAR. We estimate VAR, but we test for behavior that is consistent with this Bernoulli trials process. So we get, if you like, empirical indicators when the true realized loss exceeds the estimated VAR from the previous day. And these should behave like a realization from a Bernoulli process, the so-called Bernoulli trials process. The usual, I think the favorite binomial test is the binomial score test. Look at it or look up a standard statistics textbook where you would compute this binomial score statistic and you'd reject the Bernoulli hypothesis at the 5% level if basically this statistic was bigger than a certain percentage point of a normal distribution. But there are one or two different binomial tests. You can have a binomial score test, a binomial likelihood ratio test, binomial Wald test. So there are one or two options, but this is one. The exponential spacings, I've written exponential spacings when I said geometric. Because these are rare events, you can effectively approximate the the distribution of the spacings by an exponential distribution. The geometric and the exponential are quite close. So the exponential or the geometric spacings, you could run a goodness of fit test, a generic test. You could do a QQ plot. You'll see various examples. Now so I fitted a lot of Gauch models. At various points, perhaps there were some warnings emitted, but we won't worry too much about this. Instead, we'll just see what came out of this. Let's see what the show roll shows. Okay, the Gauch roll. The Gauch roll. It sounds like sushi or something. The 556 refits of the model. The refit horizon 10, 5,500 VAR forecasts, standard gauge, distribution normal, and then there's some more information that we won't look at immediately. Let's look at a picture instead. So this is sort of what happens. You make the forecast. So the black line is the forecast, and you can see here that if I'd written this software, I'd have had it up here so we could be looking at the losses. This is the time series of historically simulated gains for the short put option. So the historically simulated gains from the short put option. When there's a negative gain, that's a loss, of course. So the black is the VAR, and if you see a red dot, that's an exception. So the red dots are exceptions, and the theory says that if we're doing a good job here, the red dots there should be a binomial quantity, and the spacings between them should be independent geometric, both of which are testable, but in the software, it's really the numbers, the binomial distribution that's tested. So I run a report. Here, and the type of report is the VAR report. And I'm going to look at the 99% VAR, or at least what my colleagues and I would call the 99% VAR, but which for Alexios is the 1%. And my test size is 5%. And so you get some results here. So the backtest length is 5,500. Now, I am a miserable modeler. So a terrible modeler. The alpha is 1%, so I would want 55 exceptions. Look at that. I'd want 55 exceptions, but I've got 145. So I'm a terrible modeler. Instead of 1%, I've got 2.6% exceptions. And there are some tests here, given names. So the language here, you'd have to read a little bit more if you're coming at this new to know what unconditional coverage means and conditional coverage, but you'll see some tests are being implemented, and it says reject, null, yes. This basically means this is a terrible result. So these are basically binomial tests. They've been attributed to certain authors in econometrics who suggested doing these things originally, but really they're just binomial tests. Reject, null, yes. What else? Yeah, there's another test. Reject, null, yes, which doesn't surprise me. Now, what we could go on to do is I've got this colleague who's a better statistician, who knows about heavy tails, and this colleague fits the model with T innovations, which at least deals with the heavy tails. So we could do the U-Gauch roll, and we could have a look at the VAR results. We'd get a different estimate. We'd get different red dots. In fact, my colleague doesn't pass either. My colleague is not all that great because I've basically created a pretty asymmetric situation. This works better. I've got a second colleague who says there's a lot of skewness here. We should use skewed distributions in the Gauch model. And this colleague starts to do a lot better. So their Gauch results are better, and when we run the report, we start to get no's, because this colleague is doing an even better job on the statistics. So that's the idea of the the VAR backtesting, we look at exceptions and we effectively test whether these exceptions occur as independent Bernoulli events, which would mean a binomial number, but also we want them to be independent, so there should be geometric spacings. What I won't do, or I won't describe the theory of, Rüdiger and I a few years ago, in fact, 16 years ago, 16 years ago, wrote a paper on conditional EVT, which Paul briefly alluded to. And in this paper, we put forward an idea for backtesting expected shortfall based on the violations. And Alexios has implemented it in the RU gauge. So if you delve deeper into it, you'll find this test in there, very kindly attributed to us. And it's a test based on the amount of the exception. So looking at this picture, suppose we also estimate expected shortfall. So we'd have a second black line for expected shortfall. And every time there is a VAR exception, a red dot, we would compare the expected shortfall estimate with the amount of the VAR exception. And those discrepancies should be mean zero. And so we have a test based on that idea. Something that you could look at your leisure. What I'd also suggest is, if you're interested in this, in the textbook, at the end of the chapter, we have an example where we do a big comparison of different backtesting methods for a share portfolio. So something a little bit easier than the short put option. We compare the methods for an international equity portfolio, just to sort of see how it works. And it has 5 risk factors. It has some index risk factors. It has some exchange rate risk factors. And we compare the methods that Marius and I have talked about. We do simple variance covariance. We do simple historical simulation. We do more dynamic historical simulation using gauge with T innovations. And then we do the multivariate. So we do the method which I think is probably the best of all, proposed by Hull and White. We do the multivariate dynamic approach. And then we sort of tabulate what happens, both for the 95% VAR and the 99% VAR. And we do it over a period of 8 years, which encompasses the financial crisis. And so you see each year, let's just go straight to 99%. In a trading year, there are 250 days, thereabouts. So you would expect somewhere of the order of 2.6, this is based on 260 days. You'd expect of the order of 2.6 exceptions or violations each year, and 21 over 8 years. And so you see certain methods, they have bad years, particularly around the crisis. You see the variance covariance has some bad years, gives you too many exceptions. You see historical simulation has some really good years and has some terrible years, but it's not a dynamic approach. This is the plain vanilla historical simulation. Has some terrible years. The year of the peak financial crisis, 22 as opposed to 3. And then you see the method I sort of think is best, the HSM gauge, does a pretty good job. And in fact, at the end of the period, has 17 exceptions as opposed to 21. Too few is bad as well, because that also means you're in a sense, you're doing bad statistics. But if you're wondering why are there these discrepancies, and this is where I want to finish really, a dynamic method learns about volatility. So there's a dashed line and a dotted line. A dynamic method learns about volatility. A static method doesn't. So the dotted line is plain vanilla historical simulation, as explained by Marius, whereas the dashed line is a dynamic historical simulation with my best option, the multivariate version. And what happens? This is Lehman Brothers. Once again, this is Lehman Brothers. And so historical simulation, we come along and there's a VAR exception. I've got it pointing the other way because I'm using my convention now. And so we have a VAR exception, okay? the dynamic method begins to learn. The dynamic method increases its view of volatility. And then comes Lehman Brothers, and for both of these methods, the Lehman Brothers day is a VAR exception, okay? But at this point, the dynamic method really learns, and it takes off. And so the conditional quantiles become much bigger, whereas the historical simulation really doesn't learn, it just edges up. And it's hit by all these aftershocks. And so every time you see a circle, that's a VAR violation for historical simulation, whereas, in fact, there's only one, actually I should be more careful, there's only one violation for this method. So, but of course, this relates to short time periods, short horizons, and arguably how much of this story carries over to the insurance context is something to discuss depending on how you go about validating models. It's 12:05. So, and I am going on the excursion, so you can grab me on the excursion, but I think Francois wants